Assalamu alaikum. So in this video, I will discuss the graphene and a magnetic field. So we know that graphene is a two-dimensional quantum material, uh, and the famous two-dimensional massless Dirac equation of graphene is given by this equation, and which Vf is the Fermi velocity, tau is the pseudo-spin polymatrices, and Q is the momentum of the Dirac fermions, the x and y directions. Here Xi represents the Wally degree of freedom. So this is the basic equation of graphene, and kx and ky momentum space. So now we want to apply a magnetic field to this monolayer graphene and the z direction. So we applied the magnetic field which is perpendicular to the sheet and the z direction, and as we know that when we apply a magnetic field, we introduce the Landau gauge for the magnetic vector potential, which is given by this equation. So utilizing the parallel substitution, we can write the momentum as given by this equation, in which E is the electronic charge of the charge carrier, C is equal to 1 for simplicity, which is the speed of light, and h bar k is the momentum of the Dirac fermions in the absence of magnetic field, B. Therefore, for a single valley, the Hamiltonian can be written as we know that the poly matrices, the pseudo-spin poly matrices, we can write the Hamiltonian of the graphene in this form, right? So in terms of spinors, we can define our wave function. So psi A and psi B is the wave function of the spinor A, spinor B, and which is directly related to the sublattice A and B. So applying the Schrödinger equation, H operator on psi, which is equal to E psi, we obtain this relationship. And now we can define the two ladder operators as follows. So this term, which is and this equation is given by this term, is represented by A multiplied by some constant values, and Eigen is represented by this equations, where LB is the magnetic length, which is equal to square root h bar over EB. Now the Fock states of the harmonic oscillator is denoted by n, where n is equal to 0, 1, 2. These ladder operators satisfy the commutation relation A Eigen equal to 1. And we know from the basic quantum mechanics that when A is acting on the state n, then it is equal to n square root state n minus 1. And similarly, when A digger is acting on state n, it is equal to square root n plus 1 or state n plus 1. So our eigenvalue equation at the k point or at the k value becomes like this. Now, we apply this on this state and E on this state. So these yield two equations as minus iota 2 square, which current we have where LBA psi V equal to E psi A. And similarly for the other equation, we have this. Now substituting this equation into this, or this equation into this, we obtain this value. So here Eigen A is acting on psi, so Eigen A is equal to n, and this equation can be written in terms of the Landau level quantum number n is. So here T represents the uh, T equal to 1 is basically +1 is equal to the conduction band, and T is equal to -1 is equal to the valence band, and represent the Landau labels. Vf is the Fermi velocity, and B is the magnetic field. H bar is the Planck's constant. So this is the basic dispersion relation of the graphene. Now, uh, if we look at the spectra of the graphene and the absence of magnetic field, we know that graphene is a um, two-dimensional material, and whose energy eigenvalues are linear nk. So we obtain the linear if we plot the E versus K for the graphene and the absence of magnetic field B, we obtain the linear dispersion relation. If we apply a magnetic field in the Z direction, then the energy levels are quantized, and we have the quantized value of the eigenenergy. So this is the Landau level, zero Landau level energy. This is the n is equal to 1 Landau level, n is equal to 2 Landau level. Similarly, n is equal to -1 Landau level, n is equal to -2 Landau level. This is basically the valence band, and this is the conduction band energies. Now we want to find out, now we want to draw this dispersion relation as a function of magnetic field B. So for magnetic field B from 0 to 10, we plotted the eigenenergies as a function of magnetic field, and we obtained these dispersion relation for the K and the Kaplan values, which are basically symmetric or equal to each other. So this is the dispersion relation of graphene. Now we want to find out the eigenfunctions of the graphene in the presence of magnetic field. So the wave function of the system in terms of the two spinor is given by psi A and psi B, which we can define the AB sublattice as basis A is psi B equal to beta n, and psi A is equal to alpha m. So applying the system Hamiltonian to psi, as we already done for the eigenvalues. So we obtain this relation and this relation. From the above equation, it is clear that m, which is the excited state, is equal to n minus 1. So, and beta is equal to iota ta alpha. This is if from this equation, the beta is related to alpha 2 by this equation. So now we can write the eigenfunction at the K value or for the K point, which is given by this equation, which is alpha m beta n. If we normalize this equation, we obtain the eigenfunction for the K value as given by this equation. So we know that the zero Landau level with n is equal to 0 deserves special attention and to be treated separately. And if n is equal to 0, the first component is 0. If we put n equal to 0, so this component is 0. And we find that the 0 energy state at the K value is entirely due to electron from the B sublattice. And in this case, the solution of the eigenvalue equation yields an eigenfunction. So we have the state due to the electron from the B sublattice, and this state for the 0 state. And similarly, we can plot the, we can drive the equation for the Kaplan value, which is given by this equation. So, and similarly for the K and Kaplan value, the eigenvalue, the eigenvalue function can be written as. So these are the wave function for the K value, and this is the wave function for the Kaplan value, where n is an orthonormal Fock state of the harmonic oscillator, and alpha nt and beta nt are given by these equations. So for n equal to, n is not equal to 0, alpha nt is equal to t by 2, where t is the band index. So we noted the zero energy state at the K value are restricted to the sublattice B, whereas those at the K prime value have a non-vanishing value only on the sublattice A. So for the K and K prime value, the index xi has been defined so that xi equal to 1 is equal to -1 respectively. And the next section, we will explore the electronic property of the material of the graphene family, stagger two-dimensional semiconductor material, especially as we switch on the spin orbiting interaction. Thank you very much.